Hey Ramblers! This video covers chapter 12.6 in our textbook and deals with the volume of spheres. After watching this video, you should be able to calculate the volume of any sphere once you know the radius. Okay Ramblers, I hope this helps and thanks for watching. A sphere is probably one of the most commonly known 3D objects, and it's just a set of points in space that are all equidistant from a given point called O. So it's like a 3D circle. And we've talked about this total area of a sphere, and that of course was 4 pi r squared. But the volume of a sphere is going to be 4/3 pi r cubed. Now it's easy enough to get these two formulas confused, but just remember that volume will always be a cubed unit and an area will be a squared unit. So the volume of a sphere is 4/3 pi r cubed. Let's make sure you get that in your notes. And just for your quick reference, there's the total area of the sphere as well. Alright, since we're on this topic, let's also remind ourselves the total area formulas for a hemisphere, and we'll also look at what the volume of a hemisphere is, even though it's not brought up in the book. Now a hemisphere, as you recall, is just half of a sphere. So when the sphere is cut in half, it introduces a new plane, which is the base of the hemisphere, and it's just a circle. So the total area and lateral area of a hemisphere is what we covered in an earlier section, and LA of hemisphere is just 2 pi r squared, and because we're adding on a circular base, the total area is 3 pi r squared. Well, the volume of a hemisphere is going to be closely related to the volume of a sphere. The volume of a hemisphere will be 1/2 of the volume of a sphere. So when we simplify that, we get 2/3 pi r cubed for the volume formula for the hemisphere. Now be careful. Once again, the radius can also be represented as a height in a lot of problems, so be aware of that. Okay Ramblers, thanks for watching, and I hope this helps. Number 13 on page 591 can be difficult to envision, but they tell us that we have a cube with 1,000 cubic meter volume. And they want to know the volume of the largest sphere that can be inscribed inside the cube. So we're going to have something that looks like this, where the sphere will be touching each center of the cube. So let's take a cross section of that, because it'll bring it down to two-dimensional geometry. I think we'll have a little bit of an easier time with that. Since the volume is 1,000 cubic meters, we know that each side must be 10 meters. And if we try to find this sphere, I'm going to start by drawing a radius. Now the radius is going to be an apothem of the square, so it's going to bisect the side, and I'll have two sides that are 5, or I'm sorry, I'll have two parts of the side that are 5 and 5. And if I draw the hypotenuse, I've got a 45, 45, 90 triangle, because the radius of the square will bisect the square's right angle. So if that means the radius of the circle is also 5. So if I wanted to calculate the the volume of that sphere, it's going to equal 4/3 pi times that radius of 5 cubed. If I multiply that out, I get 500 pi over 3, or the decimal approximation is about 524 cubic meters. All right, let's take a look at part B on the next slide. In 13b, now the sphere is outside the cube, and so we have to figure out the volume of the smallest sphere that can be circumscribed about the cube. So each one of these corners of the cube will be touching the sphere, the inside of the sphere. Alright, so let's take another cross section and put the sphere inside it. Put the cube inside it. Now, we have to be careful, because since the corners are touching the sphere, the diameter is going to stretch from one corner of a cube to the opposite corner of the cube. So the distance formula in 3 dimensions, as you'll recall, is x squared plus y squared plus z squared. So we're going to get a total distance, or a diameter, of this cube, which is going to be equal to 10√3. Now, that means the radius will be 5√3, And so as I try to calculate the volume of that sphere, that's going to equal 4/3 pi times 5 root 3 cubed. Simplifying that, we get 1,500 pi root 3 over 3. The decimal approximation for that would be about 2721 cubic meters. Okay, Ramblers, let's take a look at another one that sometimes gives trouble, and that's number 11. Okay, we're looking for the total volume, which of this thing they say is a mini submarine. And so we're going to add, it's going to be done in 3 parts. We're going to have the volume of a hemisphere, and then we're going to add on the volume of a cylinder, and then finally we're going to add on the volume of a cone. And when we get those 3 parts, add them together, we should get our total volume. So they tell us in the problem that the cone has a radius of 3, which means the cylinder has a radius of 3, which means the hemisphere has a radius of 3. They kind of sneak that in there. So the volume of the hemisphere is going to be 2/3 pi times 3 cubed, plus the volume of the cylinder, which you recall is the area of the base, which would be 3 squared pi times the height, which they tell us is 12. And then we're going to add on the volume of the cone, which is 1/3 the area of the base times the height of 4. So let's simplify that and we'll get our final answer. So all that simplifies to 138 pi. In part B, they'd like us to find the surface area of this. So we'll take the surface area, or the LA of the hemisphere, and they'll add on the LA of the cylinder, and finally we put on the lateral area of the cone. And when we figure all those 3 out, we'll add them together. The lateral area of the hemisphere is just going to be 2 pi times 3 squared. The lateral area of the cylinder is just going to be the perimeter of the base, which is 6 pi times the height of 12. And finally, the lateral area of the cone will be 1/2 the perimeter of the base, which is again 6 pi, times the slant height, which I can see there's a 3, 4, 5 triangle, so the slant height is going to be 5. And when we simplify this, we get 105 pi. Okay, let's take one more look at number 10, because that's caused trouble in the past, and then we'll wrap it up. Okay, number 10 tells us that the radii of 2 spheres are in the ratio of 2 to 5. So what's the ratio of their volumes? Well, you recall from chapter 11 that the ratio of areas was equal to the ratio of sides squared. Well, that's when we were dealing with two-dimensional thing like area. When we're dealing with the volume is a 3-dimensional. And since we're cubing volume, when we find the volume of a sphere, we're going to cube the respective radii in order to find the ratio of the two volumes. So I'm going to have 2 to 5, and I'll cube that, and that will give me 8 to 125. Now, if you want to see that worked out, you could have said that that also equals sphere 1 would have a volume of 4/3 pi times 2 cubed over the volume of sphere 2 would be 4/3 pi times 5 cubed, and of course the 4/3 will cancel, the pi's will cancel, and you'll be left with 2 cubed over 5 cubed, which is what we have already. The ratio of the surface areas is just going to be back to side 1 over side 2 squared. So we're just going to take the radii 2/5 and square it, and we'll get 4/25, which is the right answer. Alright, Ramblers, thanks for watching. I know this was a long tutorial. Thanks for watching.